All right, so our buffered solution is going to be made of the NH3 that's already there and the NH4 plus that I'm going to form by reacting with HCl. Now, the Ka, or the pKa that I need in my Henderson-Hasselbalch equation, I need a Ka. But this is finally, and we did some of these on Monday when we didn't have to do them. We don't have a Ka for NH4 plus, but we have a Kb for NH3. So this is where we get to do that trick. Where Ka then will be equal to Kw divided by Kb, in this case 1.0 times 10 to the minus 14 divided by 1.8 times 10 to the minus 5. 2 sig figs, we're looking at 5.6 times 10 to the minus 10. So here in a minute, we're going to apply the p function to that number, 5.6 times 10 to the minus 10, and it's going to go right there. That works. Oh, well, there's the p function applied. So 9.26 is going to be this number right here. It's always fun when you're like, oh, we got a new number. And I think the next line says, yeah, it's a good choice. And what I mean there is, remember that the closer this is to 1, sorry, the ratio of 1, they're even amounts of base and acid. If they're equal, this ratio becomes 1, log of 1 is 0. So if that's an ideal situation, ideally then your target pH should be close to your, within plus or minus 1 pH units of your pKa. All right. So there's our Henderson-Hasselbalch equation. Yeah, okay. Remember that kind of an alternate form is this, where instead of the molar concentration, we could go with moles. So we can go with moles here, N of base and N of acid. The other thing you can see I've done here is moved the pKa onto the side with the pH. You get pH minus pKa. And then I kind of showed you how if you're trying to get to, well, we can remove the log function by taking 10, you know what I'm saying, 10 raised to that power. So this is kind of like what we did last time. So, where does that get us? So, keep in mind that the base here is going to be NH3, and the acid here is going to be NH4 plus. And it's like you might think, like the more that we convert NH3 to NH4 plus, we're going to lose NH3, and NH4 plus is going to build up. So what's going to make that conversion is that strong acid, HCl. So here's a warning, and you're going to see something like this probably on a test, that the HCl doesn't appear in the Henderson-Hasselbalch equation because it's not the conjugate acid. Okay, that's not that acid. Okay. It's helping to form that acid. Okay, the acid that we're going to make by reacting NH3 with NH3 with HCl is NH4 plus. So we're going to have to do some subtracting from our NH3 because part of it's going to be used to make NH4 plus. I call it counting beans. So some of it's going to go away. The other thing we need to take into account is as we add some of this HCl, we're supposed to come up with how much HCl do we need to add to convert NH3 to NH4 to make this relationship true. We're going to have to consider that volume of HCl that we're going to be adding. Okay. So notice here, this actually, I want you to know, I'll just do it this way. Specifically, our weak base is NH3, our strong acid is HCl, The conjugate acid it's going to form is NH4 plus. Okay, plus chlorinates. But this is going to be in limited supply. It's all going to be consumed, and this actually, you got to have some left over. You won't want to convert it all, or you're going to end up with a non-buffered solution. So we need to know the number of NH3 that will be converted, number of moles of NH3 that will be consumed or converted. And then once we come up with that, we'll know the moles remaining by subtracting that from what we start with. And the moles of NH4 formed, NH4 plus. So what do we have first? Well, over here, we had a volume of 150 milliliters, a molarity 0.123 molar. So we're going to use those. If we put as our starting term 150 milliliters, 3 sig figs. The next term, oh, I know. So we haven't done this yet. This actually is kind of nice. Notice I'm not going to convert it to liters. I'm going to keep it in milliliters, and then what I'll end up with is millimoles. So from the molarity, 0.123 molar means 0.123 moles per liter. It also means 0.123 millimoles per milliliters. So now our milliliters cancel out millimoles of NH3, which looks great. 3 sig figs, you're looking at 18.5 millimoles of NH3, what you start with. This is kind of a nice little convention to go with. So that's what we start with. So this is what I've been telling you. There's your weak base, there's your strong acid, a one-way arrow, and the NH4 plus is the conjugate acid that's going to be formed here to make our buffered solution. So if we let X be equal to the millimoles of HCl that's going to be added, notice the stoichiometry here is 1 across the board, then that will also be equal to the millimoles of NH3 that will react, and will also be equal to millimoles of that conjugate acid that's formed, NH4 plus. Okay. So, seeing what that looks like when the dust finally settles, or at equilibrium, the millimoles of HCl, 0. Millimoles of NH3 you have left would be what we started with, 18.5 minus X, and the millimoles of NH4 formed would be X. All right, see how that works into our Henderson-Hasselbalch equation. Well, according to our Henderson-Hasselbalch equation, this is the ratio of base to acid will be equal to 10 raised to the pH minus pKa. We know the target pH, we know the pKa, okay? So actually, can't we just take those, that 18 point whatever minus X and X and plug them in there? We sure can. So 18.5 minus X, which is your NH3 millimoles present, over X, which is your millimoles of NH4 plus formed, needs to be equal to 10 raised to the pH minus pKa, 10 raised to the 9.50 minus 9.26. And somehow we need to go ahead and clean that up. I would probably work that out, write down a number, and then I would probably kind of, what I say, cross multiply to kind of flatten it out. But we don't have to use the quadratic. It's going to work just fine. Okay. So solving for X, you're going to get a value for X, 6.75 millimoles. Which is not quite done there. So that would be the millimoles of HCl added. Okay. So we know the molarity, and so we should be able to get volume. So 6.75 millimoles, and from the molarity, we have 1 milliliter will contain 0.0883 millimoles of HCl. So 3 sig figs, we're looking at 76.5 milliliters of HCl solution. Will get you the chemistry that will create the buffered solution you want to get a pH of 9.50. Tomorrow's lab, it's almost like I wish I had one more lecture day before tomorrow's lab. We'll do fine because we're going to start the next part. But tomorrow's lab and titrations, actually, this is something that you need to know your way around. Okay, so that was the second way to create a buffered solution. And I haven't made any progress. I think I still just have 3 maybe of the 7 that are assigned that will be due on Friday. We'll be doing Friday. But I should have time tonight, hopefully, to knock out those other homework. Okay, so that's my goal anyway. All right, on with part 8. See how far we get. So you guys did acid-base titrations in Chem 1, and we're just actually kind of build on that. The type of titration y'all did in Chem 1 was a classic. It was a strong acid with a strong base. So it was HCl, probably in your as your what we call the titrant in your beaker, and in your burette was NaOH, sodium hydroxide. But actually, there are 4 possibilities for acid-base reactions, acid-base titrations, and they go like this: strong acid, strong base. That's what you did in Chem 1. Weak acid, strong base. Strong acid, weak base. To me, this kind of sounds like what we just finished up with that last example. We had the weak base NH3, the strong acid HCl. The 4th one, and actually won't spend much time because it's the hardest one to sink your teeth into for sure, and that would be a weak acid and a weak base. That's about it. Anytime you write an acid-base reaction, they have, if you look on the product side, you should be able to pick out 2 conjugate acid-base pairs. We've kind of had some work at doing that. So remember, this is actually, if you go, the way this works is if you go across, you can pick out the conjugate acid-base pairs here. They differ by a proton. The acid has 1 extra proton, the base does is minus proton. So let's look at examples of all 4 of those. Acid-base reactions, acid-base titrations. In this one, clearly a strong acid, strong base, okay, goes to form, we're going to call this a salt, NaCl and H2O. Looking on either side of the reaction arrow, you should be able to pick up 2 pairs. So focusing on the chloride ion, over here it has a hydrogen, so HCl is actually the conjugate acid, the conjugate base with Cl minus. Over here the NaOH, OH minus is the base, and H2O is the conjugate acid. We could go ahead and knock out things that appear on both sides. I'm thinking looks like sodium and the chloride ion can both go away. In that case, it just boils down to H plus OH minus goes to form H2O. That was strong acid, strong base. What about a weak acid, strong base? So a good example of a weak acid, this is acetic acid, CH3COOH, reacting with a strong base, NaOH. Weak acid, strong base. Okay, going to form, this is sodium acetate, and water. So seeing how things kind of break apart, notice that we're not showing, the only thing we're showing breaking apart or ionizing entirely is your NaOH. Oh, actually, sorry. And also sodium acetate. So here in a minute, when we cancel common ions, spectator ions, one thing that's going to cancel is your Na+. So picking out the pairs on either side of the reaction arrow, we have acetic acid and acetate, differ by a proton. Then we have OH minus and H2O, differ by a proton. Here's the net ionic equation, minus the Na+. So you have CH3COOH plus OH minus goes to form CH3COO minus and H2O. All right. And this one, strong acid is HCl, weak base NH3. So seeing what breaks apart, looks like we have the HCl breaking apart entirely and the NH4Cl breaking apart entirely. So here in a minute, looks like we're going to delete the Cl, the chloride ion, Cl minus on both sides. Identifying your conjugate acid-base pairs, HCl and Cl minus differ by a proton, NH3 and NH4 plus differ by a proton. So there's your two pairs. Again, the net ionic equation is minus the chloride ion. So that's why it has NH3 plus H plus goes to form NH4 plus. Now, I haven't mentioned it before, but your net ionic equations should balance for both mass and charge. So if I do the drip brick wall here, like we did in Chem 1 just the other day, we should have the same number of nitrogens and hydrogens, which we do, but also the charge should be the same. So I have a +1 charge over here and a +1 charge over here. Okay, the last example, we'll pick up the weak acid we had before and the weak base we used before and see what that looks like. So as far as something ionizing entirely, I think it's just this one over here, the CH3OO and the NHOO minus and the NH4 plus breaks apart. So our net ionic equation, there's nothing to cancel, is there? So looking on either side of the reaction arrow, here are your two pairs differing by a proton, CH3COOH and CH3COO-1, NH3 and NH4 plus. So our net ionic equation looks like our original equation. All right, that's the 4 options there. So whenever we have an acid and a base reacting, like we saw those 4 different examples, you can think of 3 things happening behind the scenes, and they add up to be the overall reaction of interest. We can think of the ionization of the acid, breaking apart, providing a proton. That actually, we're going to call that K1, the equilibrium constant K1, but it's really the Ka, right? The second step would be the hydrolysis of the base accepting the proton. We'll call that K2, but really that's the Kb of the base. And then we have something we have the reverse of autoionization. Autoionization was where an H2O molecule breaks apart and gives the H plus and the OH minus. In this case, we have that H plus and OH minus combining to make an H2O molecule. So it's the reverse of autoionization. Autoionization has the K value of Kw. So that's why in this case we're going, since it's reversed, it's the reciprocal. So Kw to the -1 or 1 over Kw. So one of the things we know about that is we can describe it in these 3 steps. Then the overall equilibrium constant will be these multiplied by each other. So check this out. K1 times K2 times K3 is equal to Ka times Kb divided by Kw. So, in other words then, as written, in order for our reaction to proceed from left to right, we will be looking for a big number. And to get a big number, you want your Ka or your Kb high. Remember the other day when I said it's never going to go uphill? So in other words, you're never going to have things reacting and forming a strong acid. That's going uphill. It's just not going to do. It's not going to form a strong base. It's just going to do. And that's kind of what this is getting to. Instead, it will be the other way around. Strong acid will break apart. Your strong base will break apart and do something. So that's kind of what that's talking about. When your Kas for your strong acids are very large, your Kbs for your strong bases are very large. All right. So I'm going to kind of think through what this might look like. Equal molar quantities. Equal molar quantities. So basically, it looks like this. If we have a strong acid and a strong base mixed together, but they're the same number of moles. So here's my strong acid, and here's my strong base. Okay, we know that goes to form a salt and H2O. So equal moles. So we're going to say that equal moles. Does this make sense? And that's actually, when you guys did your titrations in Gen Chem 1, that was your endpoint. That's your endpoint. If you do that, then this is all used up, and all you have is this over here. So, what's that over there? Salt and water? Okay, there's nothing to make it acidic or basic. That's my point. This is going to be neutral. Okay, no interesting chemistry going on. Neutral on the pH scale is 7.00. Well, let's mix it up a little bit. Okay, now I'm going to go weak acid and strong base. So here's the deal. And see, did we do these? No, that we did ammonia and HCl, but it's kind of similar. What this is going to do is your strong base is going to create the strong base is going to create the weak base conjugate of that weak acid. Okay. Again, equal moles. And this is entirely going to be gone. So this is all gone, just like this down here. But now, we don't just have an innocuous salt. You have basically formed, again, no pun intended, you have formed the conjugate base of that weak acid. So this thing is going to float around and it is going to be basic. Again, it's like at the equivalence point. Equal molar is at the equivalence point, but it's basic. You have some little more interesting chemistry going. So is that above 7 or less than 7 in this basic? Exactly. Yeah, gonna make a basic solution. Okay. And we can actually, and we will do some calculations to come up with what the pH of that will be. All right. There we go. And this one, strong acid and a weak base. Okay. Again, equal molars, equal molar quantities, which just means that this will all be gone, all used up. But what's going to happen is this weak base of yours is going to accept a proton and form the conjugate weak acid. Okay, so that is why, that's what's going to drive the pH of your solution at the equivalence point. The